So lines model many natural behaviors that happen in life and society and whatnot. But in the last section we talk about quadratics, and the reality is that also models many things, but I want you to know there are other models too. So in this section, section 4.8, it talks about polynomials in quadratics, so lines, quadratics, or higher order polynomials. We're going to add, subtract, and multiply them. And we're going to graph and use the graph to find some values. So let's talk about the differences and similarities between polynomial, linear polynomial, quadratic polynomial, and cubic polynomial. So clearly these are all special types of that. Okay? So let's define a polynomial. What is a polynomial? It is a mathematical expression where the variable has whole number non-negative exponents. So math expression with the variable having whole number non-negative exponents. Yep. Okay. And then, and notice I said the variable has those, but the numbers in front of those variables, that's not a stipulation here. So it's just the variable, the varying quantity, has whole number non-negative exponents. Okay, and then a linear polynomial is one where the highest exponent on the variable is 1. So it's still a polynomial, so it satisfies this, but in addition to that, the highest exponent on the variable is 1. Now it still is non-negative, so that means the exponents are 0 and 1 on the variable. And we know this, the linear polynomial looks like the form, y equals the initial amount plus the constant change times x, and silently or implicitly, this is meant to be 1, and this has a variable to the 0 power here. So x to the first and x to the 0 here. So here's the linear equation where the highest exponent on the variable is 1. Quadratic polynomial is a polynomial, so it satisfies this blue business, where the highest exponent on the variable is 2. Okay, and we know that the general form of a quadratic from section 4.7 is y equals a number of x squareds, b number of x's, plus c, and this would be x to the 0 implied or implicitly. And notice that the variable on this x is implied to be 1. So it's a math expression where, or with the variable having whole number exponents, so 2 and 1 and 0, where the highest exponent on the variable is a 2. Got it? There's a quadratic. A lot of people ask me why it's called a quad, and that is because of the quadrilateral, right? That it's basically an x by x. Anyway, cubic polynomial is very similar, except the highest exponent on the variable is 3 because it's cubes. So quads, quadrilateral, and cubes, cubic. So this would be highest exponent on the variable is 3. So the general form of this would look like a number of x cubes plus b number of squares plus c amount of x's and plus d. Where this is implied to be x to the 0, here's x to the first, silent 1 here. And so now what you see is a math expression with the variable having whole number non-negative exponents, and the highest exponent on the variable is 3. Cubic. And this, right, would give us a cube. So let's take a peek at example 1. It says identify the polynomial. Indicate if each of the following expressions is a linear polynomial, quadratic polynomial, cubic polynomial, just a polynomial that doesn't fit into one of these special categories, or not one at all. All right, I like to go with the low-hanging fruit and identify ones that I already know, like number 1 and number 6. So when I look at this, I look at number 1 and I'm like, that is a linear polynomial. Let's write that down. Do we have any other linear polynomials where the highest power is 1? Nope, not seeing it. Okay, so linear's done. Now maybe we can go with the quadratics where the highest exponent is 2, and I certainly see this one here. Yes, so this, and as a matter of fact, we actually graphed that in the last section. Good. Do I see another one? I see one right here. Whole number exponents. Again, every time I see an x, I think a 1. Exponent, power. And even though we have a negative in terms of the constant coefficient, that is not the variable. And remember, this is the highest exponent on the varying amount, so the variable. And here the variable is x, so this too is a quadratic polynomial. Okay, now I'm going to go to the ones that are not polynomials. So variables having whole number non-negative exponent. Okay, so I see here that's a negative exponent, and that is breaking the rules. So not a polynomial. Not a poly. Got it. Is there another one? Here. 2.4 is not a whole number. That is a whole and a partial. 4/10 is a fraction of a piece or a portion of a piece. So this is not a polynomial. Very good. Let's see here. The highest power here is 17. So it's not linear, quadratic, or cubic. This is just a pure polynomial, because every exponent is still just a whole number. So it didn't break any rules of being a polynomial, the variable having whole number non-negative exponents. It's good to go. Polynomial. Now this one though, that doesn't break the rules of being a polynomial, and the highest power is a 3. So implied exponent on 1 on x is 1, and this is a cubic. Yeah? What about down here in number 8? So I see another implied exponent. Got it. Is this a polynomial? Do we see any exponents other than whole numbers that are non-negative? I think they're all good. So this is a polynomial, and I see the highest power here is 3. So the highest exponent when written out in all of these added and subtracted terms is cubic. We'll talk about multiplying in a bit. But right now, all of these, so I want you to notice that every single example in example 1 are terms that are being added and subtracted. There was no multiplication and division here, and that is pretty key for identifying it using these stipulations or qualifications. Okay. A few remarks about this. Right. We treat objects such as x squared as though they are like other x squareds. So also known as terms. Such as x squared, as though they are like other x squareds. And what I mean is they have common units. Their units are in common. So apples and apples, squares and squares. So we can count up more squares. So we really do treat them as though they have the same units. And so we can add them and subtract them, like in our unit analysis. Another thing that's remarkable, polynomials do not just stop at cubics. They can have very high exponents, like there was a 17 in that example. And we use them if we need them. You know, these are extendables. So polynomials do not just stop at cubics. So if we need quartics, we'll create them if it's a better model for a given situation. Okay, so polynomials do not just stop at cubics. They can have very high exponents if we need them to. And my last remark before we do another example is we did lines, right? And now we're looking at higher powers. So entire chapter on lines. I mean, we dedicated a lot of time to those lines, and now we'll look at more models, higher power models. Okay, let's open the gate to having more information about a situation. The more information, the better our decisions get. The better our model gets, the more realistic it is. Example 2, sums and differences. All right. Compute the sum of negative 7x squareds minus 2x's plus 4 and 10x squareds minus 8x's plus 5. Sum, what does that mean again? Add? Okay, we are adding these together. Well, if I look at this, I have negative 7x squareds plus 10x squareds. That is 3x squareds. negative 2x's and an additional negative 8x's, so altogether negative 10x's. So I'm minus 10x's. Got it. And 4 plus an additional 5 is plus 9. Got it. So we just took two quadratics and we added them together to create a new quadratic. So this one plus that one made a new one. Okay, so let's take a peek at some enrollments. For women and men in U.S. colleges, this would be self-identification, can be modeled by the following equations, where T is the number of years since 1980. Okay, so here's a model for the women, here's a model for the men in millions of enrollment in college. Find an equation of the sum of these two functions, Okay, so let's see here. Let's write W plus M, because we're, again, sum means add, is equal to, oh boy, we have 0.17 t's plus 0.076 t's. What's 0.17 plus, let's see, 0.17 of them plus 0.076 of them makes 0.246 t's. And then we have 5.59 million plus 5.38 million. Oh, how much is that? 5.59 plus 5.38. That is 10.97 millions of people. Got it. We just added them together. Here are the t's, and we treat them like terms. And here were the non-t's, and we treated them like terms. Compute W plus M of, so this is function notation. Okay, so this is a brand new equation in part A. And this is saying the input is 34. So this is saying T equals 34. That's how I translate this, because it's function notation. So we're not talking about multiplying it. We're talking about take W plus N of 34. So, and then describe what it means. Okay, so let's plug that in. 0.246 34 times plus 10.97. 0.246 times 34 plus 10.97. Okay, that is equal to 19.334. Okay, well, T is years since 1980. So what year is that? 1980 plus 34 years, 2014. In 2014, there were about, this is millions, so enrollment in millions, 19,334,000 women and men. This was not very inclusive, just parsing out women and men, so I'm actually going to write that. Sorry if you are left out, or if you had to make a choice between these two, because those were the only two you could choose. In 2014, there were about 19,334,000 women and men enrolled in U.S. colleges within the United States. Got it. Find the equation of the difference of the two functions. Now, it doesn't really say, oh, in this one it says women take away men. So let's do that difference. Okay. So, difference, right? That means subtract or find the change. And change means subtract. So, we'll go women minus men. So now we have 0.17 t take away 0.076 t's. 0.17 take away 0.076. That makes 0.094 t's. And then we have 5.59 take away 5.38, because those are like terms with like units. And that was 0.21. So plus 0.21. Got it. Found the equation for the difference of these two functions. Compute. Okay, so here's the function in C, part C, when t equals 34. Okay. Yep, let's do it. Let's compute that. So, what do we have? 0.094 34 times plus 0.21, all in millions. Okay, I am putting that into my calculator, and I get 3.406. Oh. In 2014, there were about, because remember, models aren't perfect, they're just really good estimated guesses, but they're never perfect. There were about 3,406,000 more women than men enrolled in United States colleges. Interesting. I wonder how many more women than men were actually in the United States in 2014. Could just because there's more women, or it could be because they literally aren't educated yet and need to get educated. Okay, in the next video, we're going to start multiplying. So we just did some addition and subtraction. Now we're going to perform some more operations.